Lesson 8, arc length of a plane curve. There are times when we need to find the length of a graph y equals f of x on an interval from a to b. In order to estimate the length of the curve, we can divide the interval up into subintervals and use the Pythagorean theorem or the distance theorem to find the lengths of each chord, which is the hypotenuse, and then sum all of those hypotenuse up. Consider this big idea using the function below. So approximate the length of the curve y equals 0.5 times x minus 2 squared plus 2 on the interval from 0 to 3, where delta x is 0.5. So you can see that on the interval from 0 to 1/2 for the x's, that if you calculated using the distance formula or the Pythagorean theorem, this would be 4 minus 3.125, so 8.875. This, of course, would be 1/2. So your hypotenuse would be the square root of 1/2 squared plus 0.875 squared. And then if you went from 1/2 to 1, it would be square root of, again, the difference in x values is 1/2. The difference in y value is 3.125 minus 2.5 gives us 0.625 squared. So I'm going to go ahead and start listing these lengths that I get when I square root those values. If I square root that first one, 1.00778, and this one from 1/2 to 1, I get 0.80039. I'm sure you can kind of see the pattern here. And if you would like to pause the video and just calculate all of these, that would be great. I'm just going to go ahead and fill in all of these. I'm assuming you came back and from the video or from the pause, and you were able to calculate all these values. We got 0.625, 0.51539, another 0.51539, another 0.625. And if we add these all up, you see that we get 4.08895 as our estimate. But we don't like estimates as much as we like exact values as mathematicians. So we want to find a formula that would allow us to calculate the exact distance along the curve. So here is our arc length problem. Suppose f is a smooth function on the interval ab. Find the arc length L of the curve y equals f of x over the interval from a to b. So arc length L on the interval AB, where a comma f of a and b comma f of b are endpoints. And then we need that smooth function. A function f is smooth on that interval if it has a derivative f prime that is continuous throughout the interval. So you can imagine that we are going to be summing up all of these little chords, I guess, hypotenuse. We'll be summing those up, only when we use an integral to sum them, it's going to take the limit to infinity. So it's getting smaller and smaller and smaller, and those little triangles are getting smaller and smaller and smaller, so there's less error, less error, less error, the more triangles we are using. So it gives us exact. So let's see how that's going to work. We are going to try to derive the formula. We're going to make a real easy, smooth curve from A to B here. And we're going to imagine from endpoint to endpoint, we are going to pick little points and then create our little right triangles and calculate all of those. We're imagining that this is how we would do it. Depending on what our delta x is, that's how far away these points would be from one another. And we would be calculating using these little right triangles and the formula that we just talked about. So you can see that as we go, we would just be adding up those distances. So let's go ahead and just take one and zoom in on it. This is going to be your change in X, your change in Y. This actually is your change in L, because of course this whole length along this curve, what we're trying to measure is L. So that's just a small portion of L. That's what that little d means, a small change in L. So if we were using Pythagorean theorem with our little triangle there, we would say that the hypotenuse squared equals the side squared plus the side squared. And then if we square rooted both sides, we would get this. And if we integrate both sides, now we have L. And what we're going to do underneath this root is we're going to do a little bit of algebra. We're going to factor out dx quantity squared. And so when I divide the first one by dx quantity squared, we'd get 1. When I divide the second one by dx quantity squared, we get dy quantity squared divided by dx quantity squared. So if we split these up and wrote this as dy dx quantity squared, the square root of dx squared, the square root and the squared, would go away. We could imagine going from some interval a to b, square root of 1 plus dy dx squared, and then all that would be left not underneath the root is a dx. And so we have created or derived our formula there for the the distance along the curve from A to B. So, arc length definition. If the function y equals f of x is differentiable over the interval from A to B, the length of the curve y equal f of x from A to B is this, the integral from A to B, square root of 1 plus f prime of x squared dx. If it's x equals f of y, then we would be looking at y values c to d, and the length of the curve x equals f of y from c to d is L equals the integral from c to d square root of 1 plus f prime of y squared dy. So we can do it with respect to x or with respect to y. Find the length along the curve. So now, let's go ahead and look at example number 1. And since our formula involves an integral and a derivative, we do need to take that derivative. So for this function, we're going to bring the 3 halves down, x to the 3 halves minus 2 halves. And then, of course, the derivative of -1 is 0. So the 3's cancel, divide by 2, I get 1, divide by 2, I get 2. And I end up with 2 times the square root of 2 times the square root of x, which is 2 times the square root of 2x. And then our length along the curve, and oops, it didn't give us, it's supposed to say from x from 0 to 1. I don't know if yours was left out, or if it was just mine here, but there it is back. And we are going to say the length from 0 to 1, or the integral from 0 to 1, square root of 1 plus, and then this would be 2 times the square root of 2x quantity squared dx. And typically we just start simplifying underneath the root, getting it ready so that we can integrate. And of course the square root of 2x squared, we squared the 2, got 4, square root of 2x squared gave us just 2x. Now one more time, 1 plus 8x dx. Okay. So I'm going to use u substitution. I'm going to let my u be 1 plus 8x. My du is 8 dx. So I'm going to be substituting my dx with du over 2, or du over 8, sorry. I also need to calculate my u of 0, which would be 1 plus 8 times 0. So that would be 1. And my u of 1, which would be 1 plus 8 times 1. 1 plus 8 is 9. So now when I do start to put my u values in, instead of going from 0 to 1, I'm going to go from 1 to 9. And this would be the square root of u, and then I would substitute du over 8 in. So this gives me 1/8 integral from 1 to 9 of u to the 1/2 du. Now, since we changed those limits of integration, you will not have to put the 1 plus 8x back in. You don't need to do that now because you've changed these to u values. So u to the 1/2 plus 2/2 is u to the 3/2, and division by 3/2 is multiplication by 2/3. And this would be from 1 to 9. So divide by 2, I get 1. Divide by 2, I get 4. That gives us 1/12. And then u to the 3/2 is going to be the square root of u to the 3rd. Always look at that denominator, and that's going to be your root. And that would be from 1 to 9. So now, that's a u. So now, 1/12 times the square root of 9 to the 3rd minus the square root of 1 to the 3rd. So 3 to the 3rd minus 1 to the 3rd times 1/12. 27 minus 1 times 1/12. 26/12. 13/6. And that's our answer for that first one. Now on to example number 2. Find the length of the curve y equals 2/3 times x squared plus 1 to the 3/2 from 0, and then that is to 3. That should be an equal. It might be an equal on yours. I don't know why it wasn't there. All right, so now, first thing we do, find our derivative. So we have our 2/3. We're going to bring our 3/2 down times x squared plus 1 to the 3/2 minus 2/2. That means to the 1/2, and then times the derivative of x squared plus 1, 2x. So the 3's cancel and the 2's cancel. Our y prime is 2x times the square root of x squared plus 1. And now we say that the length along the curve is equivalent to the integral from 0 to 3 of the square root of 1 plus 2x times the square root of x plus 1 squared dx. So now I'm going to go ahead and square the 2, square the x, and square that square root, leaving us with just the x squared plus 1 there. So we've got 1 plus 4x to the 4th plus 4x squared dx. And I'm going to put these in order. 4x to the 4th plus 4x squared plus 1 dx. And now what we would like to do is write this as a perfect square binomial. We're hoping that we can. And if we use 2x squared and 1, we can square that, get 4x to the 4th. A 2x squared and a 2x squared is a 4x squared. 1 times 1 is 1. So that does work, and you're able to square or cancel the square and the square root. So now that leaves us with the integral from 0 to 3 of 2x squared plus 1 dx. So now when I integrate, I get 2/3 x to the 3 plus x from 0 to 3. So that's going to be 2/3 times 3 to the 3rd plus 3, and then minus 0. So 18 plus 3, 21. Example number 3. Find the length of the curve from x equals 1 to x equals 8 and round your answer. I'm still going to go ahead and take that derivative. You could, honestly, since it's a calculator problem, you could put this in your y1 so that you know that that is in y1, and then calculate this integral. And you could just say, like y prime of x squared dx. But I'm going to go ahead and calculate y prime. So, and there is another mistake on mine. That's supposed to be 2/3. And it said 2 over x. It was not, that's not what it meant to say. So I hope that yours says 2/3. But we've got a 2/3. We're going to bring the 2/3 down, x to the 2/3 minus 3/3. And that gives us a derivative of 4/9 x to the negative 1/3. And then if we did it this way, we would say L is equal to the integral from 1 to 8 of the square root of 1 plus, and then this would be 4/9 x to the negative 1/3 squared, all underneath that root dx. Now, this is the one that I put into my calculator. I'm going to show you on Desmos. But you could have also gone one more step. You could have squared the 4, squared the 9, squared the x to the negative 1/3, which would give you x to the negative 2/3. And you could have put this in. So either one of these, or you could have done it this way, okay? But I ended up putting this one in, and I'll show you right now where that is on my Desmos. You can see I integrated from 1 to 8, square root of 1 plus 4/9 x to the negative 1/3 taken to the second power dx, and we got 7.28937. So this is approximately equal to 7.28937, which if I was rounding to 3 decimal places, 7.289 is the approximate length along the curve of y from 1 to 8. And then our last one, this one is the one that's a little bit different because it's x in terms of y, and we're integrating from y equals 2 to y equals 3. So this time we're going to be finding dx dy instead of dy dx, which is like x prime, right, with respect to y, but we don't really write it like that because we know that prime typically goes with respect, it's y with respect to x. But anyway, this is a good time to use dx dy. So think of this as 1/6, and then you're bringing the 3 down times y to the 2. And then I'm going to think of this other one, the second value, or second term, as 1/2 y to the negative 1. So I would be bringing the negative 1 down, y to the negative 2. So now divide by 3, divide by 3. This gives us 1/2 y squared, and then minus 1 over 2 y squared, right? Because negative 1/2, but then I brought that y to the negative 2 down, and it became y to the positive 2. So now when I use my formula, I'm saying the length along the curve is the integral from 2 to 3 of the square root of 1 plus, and then we put our 1/2 y squared minus 1 over 2y squared dy. So over to the side, I'm going to go ahead and calculate that 1/2 y squared minus 1 over 2y squared times itself. And we take our first one times our first one. That's going to give us 1/4, and then y squared times y squared is y to the 4th. And then we're going to take our first one times our second one there. It's actually outer times outer. That's going to give us negative 1/4. And then look, one of the y squareds in the numerator, the other one's in the denominator, they cancel. And then we take inner times inner. And that's going to give us 1/2 times 1/2, negative 1/4. And look, one y square is in the numerator, the other one's in the denominator. They cancel. And then last times last, that gives us a positive 1 over 4y to the 4th. So when we add like terms here, the negative 1/4 and the negative 1/4 is negative 2/4, which is negative 1/2. Okay, so now let's go over here and let's place that into our spot 1 plus, and then this would be 1/4 y to the 4th minus 1/2 plus 1 over 4y to the 4th dy. And you can see that you have the 1 and the negative 1/2 as like terms, so we are going to simplify those. This would be a positive 1/2 when we simplify. And now, the best thing to do at this point is underneath the root to find a common denominator. So I see 4, 2, 4, and y to the 4th. So 4y to the 4th is my common denominator. And on the first one, we would multiply by y to the 4th over y to the 4th because we want 4y to the 4th in the denominator. That would give us y to the 8th. And on the next one, we would multiply by 2y to the 4th over 2y to the 4th, giving us positive 2y to the 4th. And then the last one is already, the common denominator is already there, so it's just plus 1. And so we're going to split this up into the square root of the top over the square root of the bottom. And I want you to see that this can be written as 2 squared y squared squared, so that when you do that, you can cancel the square root and the square like that, and you're left with 2y squared in the denominator. We're going to try and write this one as a perfect square binomial. Y to the 4th times y to the 4th is y to the 8th. 1 times 1 is 1, and if I write it like this, I'll have a 1y to the 4th and another 1y to the 4th that will give us that middle value of 2y to the 4th. So then those cancel. I'm going to go to the next page with this so that I can finish it, because it does seem to be a little bit like it's going to take a little bit more of our space. Okay, so now we have the integral from 2 to 3. We have y to the 4th plus 1 over 2y squared dy. I think you could use, well, I think the best way to integrate this is to notice that you have a monomial. And so since you have a monomial, it might be easier to just write it as each of the terms in the numerator divided by that monomial. And so when things cancel, you are left with 1/2 y squared on the first term. And then this one we could write as 1/2 y to the negative 2. Okay, so that would give you a setup where you can integrate. So this is going to be y to the 3 over 3. So this is going to give us 1/6 y to the third. And then this one, when I add 1, I get negative 1. So I'm going to have a negative 1 being multiplied by that 1/2 y to the negative 1 from 2 to 3. And I'm going to simplify this just one more time before I use the fundamental theorem of calculus. I think I'm going to write this as 1 over 2y. Okay, so 1/6, and then this would be times 3 to the third minus 1 over 2 times 3 minus, this would be 1/6 times 2 to the third minus 1 over 2 times 2. So we've got 27/6 minus 1/6 minus, this would be 8/6 minus 1/4. So 26/6 minus, let's make this into 12ths. So we would say times 2 times 2 and times 3 times 3, giving us 16 minus 3 in the numerator there. So I'm going to go ahead and make that 13 thirds minus, and this would be 3/12. And I guess I could reduce that to fourths, but I'd have to put it back to 12ths anyway. So I'm going to put this one in 12ths. Then we'll have everything in 12ths. 52 minus 3 over 12 is going to be, I'm sorry, that was a 13. 52 minus 13, because I was thinking, wait a minute. I thought I got 39 here. 39 over 12. Divide by 3, divide by 3. Oh my gosh, I did it again. I just can't go right with 13 today. With the number 13. Okay, so our final answer then is 13/4 for the length along the curve of that f of x function from 2 to 3, okay, 13/4 units. All right, I think that's it, and now you should be able to do that 8.8 homework. Thank you so much.